Okay, so today we are going to talk about return-oriented programming. I have mentioned this multiple times since the beginning of this class. So return-oriented programming is one of the most important discoveries in the last, I would say, 15 years in computer security. Um, it changes a lot of things. So we will spend at least two sessions on this topic. We will say how to do return-oriented programming. We will also say state-of-art defensive techniques to defend against return-oriented programming. A little bit history about it, or usually we call it ROP, return-oriented programming ROP. So this technique, not the very generic version, was first introduced in 2005. So back then, not many people know about it. However, in 2007, CCS, the most general version of ROP technique was published. And I have mentioned this many times probably. CCS is one of the top four security conferences in academia. CCS, Oakland, Usenet Security, and NDSS. And CCS is usually the biggest one. They usually accept 150 papers every year. 10 years ago, it's very small, like 40 papers, 30 papers a year, so it's very difficult. So 2007, probably 30 papers a year, very hard. So the CCS 2007 paper was titled The Geometry of Innocent Flesh on the Bone. Return into deep sea without function calls on the x86. That was the original title in the CCS paper. And it was a single author paper from Professor Howard Shanchan. I don't really know how to pronounce his name. He is a genius. He made a lot of contributions in applied crypto, system security, software security. So when he published this paper, he was, I think he was an assistant professor at UCSD. So right now he's not with UCSD anymore. Right now he moved to UT Austin, University of Texas at Austin, which has a very, very strong computer science program. He graduated from Stanford. His advisor is the guy who proposed the identity encryption, identity-based encryption, IDE. His advisor was famous for crypto, system security. Uh, his name is Dan Bo, I think. Yeah, one of the most influential security researchers in the last maybe 30 years. So he made a lot of, so this guy made a lot of contribution to security. And when he was a professor, he decided to, he probably realized how important this work is. So he decided to do everything by himself, published a single author paper as a professor. That's kind of rare actually. Most of the professors do not do single author papers anymore. I don't have single author papers. So yeah, so he decided to do single author paper. So in this paper, he discussed how to generalize return to deep sea techniques into something even more powerful. He found out that in any sufficiently large body of x86 executable code, there will exist sufficiently many useful code sequences that an attacker can control to do arbitrary computation. Um, so this is the original paper in 2007. It was on x86. So later, this technique, ROP, was extended to other architectures as well, for example, ARM. So you can take a look at this paper. It's not very easy to understand the way he writes it. Also, I mentioned before, those big conferences, they have something called a test of time paper award. 10 years, I think Usenet is like 12 years after a conference, they will choose one paper or more from that conference and give it a test of time award to show the influence of that paper to academia and also industry. So the StatGuard paper, which proposed stack cookies, candidates we talked about received the Test of Time paper award at Unix Security. And this paper in 2017 received the Test of Time paper award again, also. Also, I don't know if you guys have ever took classes with Professor Maria Blanton. Yeah, so she actually has a Test of Time paper award from CCS. So yeah, so she was a crypto guy. She's still crypto. She still works on crypto. She actually has a Test of Time paper award from CCS. That's a huge honor. Also, there is another version of this paper published in the most prestigious security journal called TSEC. It used to be ACM transactions on system and software security, maybe? No, I don't remember what TSEC stands for, because recently they changed their name anyway. So recently TSEC changed their name to TOPS, which is ACM transactions on privacy and security. You notice that they put privacy before security in the title, which is a little bit weird. So I actually had a chance to talk with editor-in-chief in a dinner, and he told me they were just having a political fight with those data mining guys who are trying to take away privacy. So they had to put privacy in front of security. So this paper is also a good read, but this one is published 5 years after the original paper was published. So much more comprehensive, but because of it much more comprehensive, it's published much later. Usually people do not cite this paper. This paper citation is not that good, but very, very good paper. Okay, so let's talk about what is return-oriented programming. Recall that we discussed in week 4 in return to libc, or not necessarily return to a function in the C library. We can return to any functions in the process address space. In those kind of attacks, what we do is we overwrite the return address on the stack and also beyond. And from there, we can put other return address there and also arguments there. So you have been doing this in homework and also midterm. So you already know how to do return to libc. A limitation of the original return to libc attack is if we want to chain functions together and the first function has arguments, then we can only chain 2 functions together. We cannot chain anything, any function more than that, because the original return address we will put the address of the function 1, then 4 bytes. Well, if it's a 64 bits, it's 8 bytes. Higher, we have the second function address. Then we have to have the function's arguments. We can put another address here because if we put the other address here, it will resides at the same location as the argument. Well, of course, there are some tricks you can play. What if the address and the argument is the same, right? But those are very rare cases. It's not like a very generic. We also discussed that there is another case that if you are returning to functions without arguments, in that case, we can actually chain as many functions together as we want. We just put an address here 1 by 1. We don't need to put any arguments on the stack. So how ROP works is very similar to this, but on the stack we do not necessarily only put return addresses. So we do not only put the code pointers. We can also put some data on the stack. However, we are not returning the code pointers we have in ROP are not necessarily functions. Usually they're not functions. We're not returning back to any functions, no matter it's a function in your program module or it's a function in the C library. We usually return to somewhere in the .text section, but that somewhere is not a function. It's just some code snippet, just some code sequence. And those code sequences are not necessarily interpreted as a code if we start from somewhere else actually. So, and another thing is when we return to some code snippet, or in ROP we call them gadgets. The gadgets should end with either a return instruction or a jump instruction, or it can be an int instruction like an interrupt, like an int 80 or system call as the instruction. So in the original paper, actually, the authors only thought about use the gadgets with a return instruction. Later, another HCCS paper proposed that we can also utilize instructions, code sequences end with a jump instruction. So they actually call that jump-oriented attack, but they can be combined together. So with the help of ROP, we will have the ability, the attackers will have the ability to chain unlimited number of code gadgets together and do some arbitrary computation, do whatever they want. Okay. So in ROP, we chain gadgets together, usually not functions. Since these are gadgets, they are usually very small, just several bytes. You're going to see that in a moment. So functions can be big, sometimes 50 bytes, 100 bytes, could be 100 instructions or even more. But the gadgets are very small. They are just several instructions, then a return instruction or a jump instruction. And because of that, there is no function prologue or epilogue there. So the return in there is not necessarily intended to be a return. It could just be a data C3, that's a return. Right? Then we chain them together in the memory to accomplish anything we want. And those gadgets do not need to be at the continuous location. They don't have to. So the way we chain them together is very similar to the way we chain functions together with argument, without any arguments, which means the attacker does need to control the stack. But the stack doesn't have to be executable. We are going to override the stack. We are going to manipulate the stack. However, we're not injecting share-code onto the stack. We're not injecting share-code anywhere. We're just using the stack as some control information to control the flow of the program. So basically, we put data on the stack, we put code pointers on the stack. That's it. There is no code directly on the stack. We have been looking at this return instruction many times. What it does is it's going to pop whatever the ESP or RSP points to EIP. That's the only thing it does. It doesn't do anything else. Just to pop whatever ESP, RSP points to the EIP. We have been looking at this instruction at disassembly level, at say code level, but we haven't looked at this at the binary level. So at binary level, this instruction is actually just 1 byte, or could be multiple bytes if you are if there is an argument. So the most the most popular ones using the return instructions are just the byte code, just 1 byte. It's either C3 or CB. So when you say a C3 or CB in the memory, then that is a return instruction. Of course, it could be a data, but even if it's a data, for example, it could be an address in another instruction. Another instruction has a jump or whatever, then there is a C3. Then that C3 can still be considered as a return instruction, depending on where you start to interpret disassemble your code. So this is only 1 byte. So which means it's not very difficult to find a lot of C3 or CB in the memory. Even if you generate some random things, you may have some. And you may have a lot of those return instructions. So one of the reasons that so now you have a basic idea why this return-oriented programming could work is because we can manipulate the stack, so we can control the code pointers, uh, and use the code pointers. We jump to different gadgets, which are very small piece of code to help us do some small things. But if we weave them together, chain them together, it can do something quite complicated, arbitrary uh, purpose. So another question you may have is, do we really have that many gadgets there? Do we really have those many useful gadgets out there? And one of the reasons there are so many gadgets is because the instruction set, the x86 instruction set, is very dense, and the instructions are variable lengths. So some of the instructions just 1 byte. Some of the instructions 2 bytes, like the return is 1 byte. Uh, Call instruction multiple bytes, right? Because there is an argument. If the argument is 4 bytes, then the instruction is at least 5 bytes. There are instructions as long as 12 bytes. Um, I think that's what I can record. There are very long instruction at 12 bytes. Um, so let's say if you have a 12 bytes instruction, when you try to disassemble it at index 0, you get that 12 bytes instruction. But if you try to disassemble this at the index 1, you get totally different instruction. It's still valid instruction. It's not like they are not instruction anymore. They're still instruction. Of course, if you run them, they may be trigger some runtime errors. But if you just disassemble them, they're still valid instructions. That's how x86 instruction set, how dense they are. Okay. So I can prove to you how dense this is. Let's try. Let me make this a little bit bigger. So let's try to prove how dense those instruction set is. What can we do? We can just let's see. Let's go to 10 for this. Let's go to 10. Then let's just generate some random data. So the kernel will give us some random data here. Then we store them in the random file. So it would just so this one will just keep generating random data. So it's not very fast, but it's relatively secure random data. There are papers talking about if the Linux, how good is the random pseudo random generator Linux use. I do not really follow that, so I'm not sure. But it's not that bad. If you want to use this for crypto keys, probably it's not a good idea. But if you just want to get some random data, this is not bad. So we just want to generate some random data. So let's give it like 10 or 20 seconds. So we have some data there. Let's see what do we have. We have random. Okay, so this is a random data we get. It's well, that's big. It's like 200 bytes something. So using XXD, we can say this kind of format. Also, we can use XXD -i that file. Then we can get the C style of this code. So we just copy this. This is a C style. Then we just find some. Let's see. Let's find. I have a browser here. Bring a browser here. Let's just find an online disassembler. So we have here we have an online disassembler. We just gave it those random bytes. You saw that. This is random bytes. Okay. Then we try to disassemble this. Oop, this one doesn't work. Okay. So x86 this doesn't work. Then try to this one doesn't work. Then maybe the first one. Then we remove this one. Remove the first byte. It works. See? So we just have some random data, and the disassembler will consider this as kind of like valid instructions. Some of them are bad, but this is kind of like most of them will be interpreted as valid instructions. And if you changing things here, so this one doesn't work. So some of the bytes. So this one also works. So so this is a random data, and it will be interpreted as this instruction and this instruction and the other instructions. So this is a 64-bit equal to 32-bit. This is the same thing. So the instruction set is very dense. Probably the 32-bit is, I think the 32-bit is even more dense. You say the 32-bit, you do not see any bad instruction here. There is one bad instruction, that's it. There are no other bad instructions. Even for our totally random data, we're not getting many bad instructions. They are all interpreted as valid instructions. Okay, this one doesn't work. Move a little bit. Yeah, all valid instructions. Of course, those instructions, if you run them, they will trigger a runtime fault, very sure. But still, they are valid instructions. Going back to so because of this, you can say how dense this instruction set is, and you can interpret, you can disassemble this one from any location. There is no like this is an actual start of this. For example, the function is remember in one of the attacks, what we did is we try to return to the middle of the function. But when we return to the middle of the function, we're still trying to return to the beginning of one instruction. But we don't have to do that. We can even return to the middle of an instruction, and the CPU will start interpret the instruction from there. So you can say, if the CPU start interpreting things from the middle of a legit instruction, it will get totally different things. At least for the first several bytes, it will get totally different things, and they are valid. They can be executed. So that is why we always have a lot of ROP gadgets. As long as you have a stage 3 there, as long as you have a return, then anything before that, you can use them as a gadget. They do not necessarily be legit instructions in the original interpretation. That's why I said in the last class, this is kind of like a Lego. So every byte is a Lego piece. And originally, when we compile something, we have a C code. The C code is kind of like our menu. We compile something, we generate a Lego piece. And now, the attacker can take everything apart and reassemble each byte, weave them together, and build a totally different Lego piece, total different Lego thing. You know? So we are going to say how it works. So to do ROP, there are several. Let me show the next page first. There are several tools available for us. There are Pong tools can help us to automatically find gadgets. And another tool I usually use is called the ROP gadget. Not only because it can help you find the gadgets, it can also help you generate and exploit. We're going to say that later. Other tools, I don't remember other tools can help you directly generate an exploit. So ROP gadget can generate an exploit that return a share to you. So basically generate something like a equivalent to a shortcut, but it's not a shortcut. Then there is another tool called a robber for you to generate to find the gadgets in the memory space. So so ROP gadget is a tool that automatically builds the ROP chain, which return a share to you. Programmably, you probably prefer Pong tools if you want to write programs. So this is the GitHub for you to download this tool. You need to, for the homework and also the test today, you need to download this tool, you can just git clone it. Then if your box doesn't have capstone, you need to install capstone. Depends on your Python version, you probably will do a pip install capstone or pip3 install capstone. Also, you run it, you want to use it, run Python or Python 3, ROP gadget or Python. Then you put a binary name there, and it will find out the gadget in that binary. And the capstone is actually a library to do all kinds of disassembly. It can disassemble all kinds of object files based on the architecture. It supports ARM, it supports Intel x86. So it's one of the most popular disassembly programmable interface people use. So the ROP gadget is based on this. So Capstone is also an open source project.
Dr. Zhao, quick question.
Yeah.
Should we get started on those downloads now for us to keep up better, or will that not affect this class?
You can download now. We can do this together. Oh, I didn't post the code online today, so probably you can't. Yeah, you can do it. You can do it later. Yeah.
Okay, thanks.
So we will first look at the return to libc. I want to refresh everyone how return to libc works. Then we can say how return or ROP works. So remember when we started return to libc, I don't know which week was this. I told you guys it's very hard to do return to libc or impossible to do return to libc in the old way on a 64-bit machine. That's because in the 32-bit version of return to libc, we put the arguments of the functions on the stack. And the stack is what we can control. We cannot control anything else in this case. And for a 64-bit version of the programs, the arguments are in those registers, RDI, RSI, instead of on the stack. Only the 7th argument will be pushed on the stack, right? So most of the functions do not take that many arguments. So the arguments are directly put on registers. And there is no way you can directly put things into the registers, right? That's why we couldn't make it work. We couldn't make return to libc work in the first half of the class. So today, the first example I'm going to show you is how can we do return to libc with the help of ROP. Okay. So before that, let me refresh you guys how to do return to libc on the 32-bit version. So this was the code we used at the first half of the class. So there is a buffer overflow in this code. There is a val foo, which has a buffer, 30 bytes. It has gets, which take input from std_in, and it returns. And we compiled this code as there is no stack cookies. However, the stack is also not executable. So NX means not executable, NC means no stack cookies. This is what we did before. We first disassemble this, then we find out the buffer is at EBP minus 30 in hex, which is actually 48 bytes from the buffer to the saved EBP. Then we have 4 bytes of saved EBP. So what we can overwrite is from here, from the buffer to everything above. So what we are going to do is we find out the function we want to return to. In this case, we want to return to the libc function system, and we can find out its address. Then the argument for it will be placed 8 bytes higher than this one. So the exit is not really that important. We can also put another, this is like the first function's address, this is like the second function address, and this is the first function's argument. So the first function argument we want to use bin sh, which so can give us a shell. So what we did is we tried to find that string on our. We're trying to find that string in our memory space. So let's try that. So I can refresh your memory. Yeah, so this is a program we're going to, no, this is a 64-bit version. We're going to use this one. Okay. So how do we do it? We first we can debug the code for so when we debug the code, we can start it. Then we can print out the address for system. So now we have the address for the system. Let me copy it somewhere. So 830. So this is the address of the system. System is this. Then let's also find out the exit. It's not that important, but now we have the address for exit. Those are state library functions, and we can also do a memory search, bin sh, which gives us the string's address is here. So
Quick
we have,
question, Dr. Zhou.
yeah.
Is the search mem part of the Pwn DBG frame that you're using, or is that everywhere?
I'm not sure if it's part of the PwnDGB or the PEDA. I actually installed two plugins here. One is PEDA, another one is PwnGDB. So I'm not sure which is it. You can also try Find.
I've used Find in the past. It's a little tougher, but I think.
Yeah, I think that in Find you can also maybe some version of Find you can just do this without giving it. Oh, well, at least the one I'm using, you can just put a string there. You don't need to specify the beginning and end, the range. Yeah.
I have kind of a reliable range to find that now, so I guess I'm okay. But
okay,
it's nice when it's easier.
Yes. So now we just need to put everything together. So what do we have here? We have so here is 48 bytes, then 4 bytes more. Then we have this address, exit address, then the string address. So that's why our our exploit will look like something. We will do a Python. See, we just print. We just do a. This is a garbage for this 52 bytes. Then we have those three address. So each of them is 4 bytes in this case. So the first one will be the address of the function system. So it is 30 A8 E0 F7. The second one will be the function address of exit. So it's here. 70 D1 DF F7. Then we have the argument for system, which is bin sh, which F2, 52, 73, F5, F7. Then this is what we have. Then we'll just another cat. We'll give this to our variable program. Let's see. And this is supposed to return us a shell. Let's see. So it works, right? So this is how we do that return to libc attack. And of course, in return to libc, you do not necessarily have to call system. You can call other functions as well. You can open a file. You can read a file. Open read. You can. That's exactly two functions. So you can chain them together, right? However, the problem, like I mentioned many times, is we put the argument on the stack. However, for the 64 version of this, it doesn't work because the argument do not, the functions will not read arguments from the stack. Instead, they will read them from the registers. And there is no way for the attacker to directly put the argument, for example, the address of bin sh into any register. There's no way to do that. Okay. So let me remind you again what is the calling conversion for 64-bit version. Because there are so many registers, we're not using stacks that often. We're directly using registers. This will make things much faster because stack is part of the DRAM, is a memory. So the CPU has to talk with something out of the CPU. It's not on the same chip, right? So DRAM is part of on your motherboard, and it's not really on that chip. Okay. Some of the CPUs, they have some on-chip memory, but that's not the DRAM part we're using. So the CPU talk to the memory, it will be relatively slow. But if the CPU doesn't need to do that, it will put everything in on register. Register is usually SRAM in the chip, so it's very fast. It's the same. So it's the same. What should I say? Material or something. Circuit material, like the cache, like the registers. They're basically the same thing. They're SRAM. They are on the CPU. They are on chipsets. So in this calling conversion, the first argument is put in RDI, the second RSI, then RDX, RCX, then R8, R9. So R8, R9, obviously, they are new registers that were not available in the 32-bit version of the machine. So those one, RDI, RSI, RDX, RCX, they are extended versions of the EDI, ESI, EDX, ECX. If you have, so those are 6 arguments. If you have more arguments, then you have to use a stack. But if you only have 6 arguments, you don't use stack. You just use registers. A lot of other RISC architectures also use registers to pass arguments. For example, ARM, MIPS, they will use registers first. Also, the return value is also on registers. Well, 32-bit of x86, the return value is also on register EAX or RAX. So this is the first vulnerable function. We are going to take a look. What we are trying to do here is we are trying to do return to libc attack. We're not doing a very generic ROP first. Let's just do a return to libc because this is what I promised you guys. I said that we will do a return to libc in a 64-bit version. So this is the code. We have a main function. The reason I use fopen, fread here is just I want to copy everything, including the 0 bytes in the exploit, because those are useful ones for the attack. So the main function, we're not going to input anything from the arguments to the command line arguments. The main function will directly call the vol foo. The vol foo has a buffer, which is only 4 bytes and the secret level. We will find out how big it is at the binary level. Then this function will open a file called exploit. No extension, just exploit. If the file is not found, then we'll just exit. Otherwise, it will just read. I think I changed this part. It's we're reading 1,000 bytes instead of 100 bytes. For this one, actually 100 bytes is enough. But for generic ROP, we need a much bigger one. The exploit, yeah, we can still call it exploit. The exploit is much bigger than even the exploit is like 700 bytes something. So that's why I put this 1,000, the updated version. So here it's just 100. Then we just return. So this one is compiled with let's see where are we. So we are going to return to let's say 64. not comparative. Oh yeah, I did comparative the 32 as well actually. But I have two versions of it. One is return to libc 64. Another is static. If you check the make file, if you check the make file, you will see that the 64-bit version, static one, we only have the stack is not executable. Okay. However, there is no stack cookies. The static one, the only difference is we compare it with the static flag. So the C library will be directly put into this file. So if we do a ls, we can see the size difference here. The return to libc 64 bits is only 17K. However, the static one is more than 800 kilobytes. That's because the C library is here. If you do a file here, you can also notice that the 64 is dynamically linked. So if you do an RDB, you can say 64. You can say it is linked with at least those three libraries. One is the libc, one is the loader, and the other one is for faster systems. I think this one is for faster system calls. Okay. Then, if you do a file on the static one, you can say this is a statically linked file. It doesn't use any dynamic library. Yeah, it doesn't use any dynamic library. Everything is in its own address space. What we're trying to do here is we want to do a return to libc attack to this file, to this 64-bit version. Then let's take a look at the stack of this system. This is a disassembly. I can just get it here. We can do object down, return to libc 64. Then we go to the valve. So this is a valve. You can see we have the F rate. So the F rate will take the one of the argument of F rate is the buffer's address, which is so buffer's address. Which one is the buffer's address? So F rate. Oh, okay. The first one is buffer's address. So which means it should be. So the first one is RDI, right? The first argument is RDI. So then from here we can say the RDI's value is RAX value, and RAX value is set here, which is EBP minus 4. Okay, so there's no padding here. The distance between the buffer and the saved RBP is exactly 4 bytes. So therefore, the stack will look like something this. We have the buffer. From the buffer to save the RBP is only 4 bytes. Then we have saved RBP, which is what? It's 8 bytes in this case. Okay, this is 64-bit version. Okay. If we want to do return to libc attack, if we want to eventually return to the function system, at some point we have to put the function system's address on the stack and return to it, right? We need to find a return instruction, and when that return instruction is executed, we need to put the RSP points to that address. That can guarantee us go back to the system function. However, the problem is there is no way for us to set the argument, right? How do we set the argument? That is where this is the first time you see ROP here. Here we are going to use only one small gadget, and this gadget is just a pop RDI return. So this gadget has 2 instructions. The first instruction is pop RDI. The second instruction is return. Then let's think how this works. Why this will work. So at this point, we don't care where is this gadget. We just assume there is a gadget like this somewhere in the memory. And then let's say we find that address of this gadget. We put that address, which is 8 bytes of that gadget, in at here. Okay. So when we at the end of the val foo will execute what? C3, which is return. Okay. So what does this instruction do? This instruction does nothing else, just pop whatever RSP points to EIP. Okay. So we put the address of this gadget there. Then the address of this gadget will move to EIP. Right? We move it to EIP. So now what we're going to execute after this one? We're going to execute those two instructions. That's what we're going to do. So the first thing is then also after this return, where this RSP points to. The RSP will increase 8 bytes. The RSP will point to here. Now, okay. Now the RSP points to here, and we are going to execute pulp RDI. So what is RDI? It's our first argument. So what is our first argument? The address of bin sh. So that's why we put the address of bin sh 8 bytes higher than this. So next time we run pulp RDI, we're going to pulp whatever is here into RDI and set the first argument of the address of bin sh. So after that pulp, the next instruction we are going to execute again is return. And at this time, the RSP already points to here when we have the return. And that is where we put the address of system here. So now we execute a return again. Then we are going to go into the function system. And when we go into the function system, we already set up the RDI. And this is a very small gadget. So this is how it works in theory. You are going to say, sure, that this doesn't really work in reality. At least it doesn't work on my machine. Okay, if you use a different Linux box, it could work. Then we're going to say why it doesn't work and how to fix that. But do you get the? Do you guys have any questions here? Is it understandable for everyone? Okay, good. Okay.
I actually, quick question.
Yes.
So, I think I missed the point on how exactly would this be different than like a traditional overwriting like return to libc attack? As in, what advantages do we get from using this, for instance?
The difference is the original one. We never return to any code gadget. Here we are returning to a code gadget, and we have to return to a code gadget like this because there is no other way we can set EDI. That's basically the reason.
Oh, okay. No, I get it now. Okay, my bad. Yeah, setting the register. It's a 64-bit. Okay, I get it.
Exactly. We need to set the we have to set RDI. That's the key. Yeah, not EDI. RDI. So let's see how we can pull this off. Where are we? Which code we are going to do? Oh, we're going to do this one, I think. Oh, okay. Another one is to fix the problem we have here. So how everything works here. Oh, by the way, I have the ROP tool here. So the ROP tool is this one, ROP gadget. So you can just do a git clone to wherever you want. Then you can use it directly. So we're here. We can do a GDB. We can debug this program. Return to 64-bit version. So if we stop this program is running. We are at main function right now, actually. The first thing we need to find out is can we find a string being sh? We still need a string being sh, right? Also, we need to find out the system function address. So let's do a p system. Now you can say this is 64-bit version, and this is our system function address. This is the address we have. Okay. Then we also do a search memory to find out that string being sh, and there is a string there which is at this address. Okay, I already write it down. The next thing is we need to find out a gadget which is pulp RDI return. So that is where we're going to use our tool. I think it's better use Python. I'm using Python 3. Depends on the system you're using. You probably just use Python 2, not necessarily Python 3. Then the script is called import. This is a script we're going to use. Then we can directly do this. We can do a binary, and we are going to use our own binary. So we're trying to find out in this binary how many gadgets we can find. So this will be the first time you see those ROP gadgets. And you say, with this, we find out 67 unique gadgets. So let's take a look at those gadgets. You'll notice that the last instruction of those gadgets. So this is the address of those gadgets, and this is the disassembly code. We're not really showing bytes here, but you can say they always end with return or jump, or it could be a interrupt, like an int 80. So here we do not find any int 80 actually. Okay. So this tool is very powerful. You can search all kinds of things. For example, you can do help. So there is something called Oni. I remember. Yeah, it's a Oni, for example. There's an Oni. We can search Oni, then we can search patterns. Like this. Pop return. No. Like this. Nope. Let me Google really quick. It's not telling us how to, because this is key, but it doesn't say what should be the key look like. There's my browser. This one. Gadgets only. Let's see. Example is only. Not really showing an example here. Oh, okay. For example, if you want to find out, a gadget that has a pulp, then a return, you don't really care which register it used, you can use this syntax. Then it will find out, oh, in this case, we don't have one. Huh? That's weird. We do have one here. We do have a pulp 15. Why it's not working?
Do you need to have a wildcard in there for?
I don't think so. Yeah. Hold on. I think it's still maybe a syntax error. I just saw it somewhere. Oh, yeah. You do not use semicolon there. Yeah, still a syntax error. You have to do this. Okay. So let's say if we will find out something, okay, ended with pulp and return, then it gave us all those instructions, gadgets that end with pulp return. And if you want to find something with 2 pulps and a return, then you can just do this. You can find with 2 pulps. Ooh. No, Oh, I'm not familiar with this syntax, I guess. Okay. But anyway, this is the one you can use. And also it can generate, another thing is other tools doesn't have, it can generate a ROP chain for you to get the share directly. You just give it ROP chain. Oh, this one doesn't work. They were not able to generate a ROP chain there. Because this one, we don't have enough gadgets, so it cannot generate a ROP chain. I can show you another one. What is the biggest thing you can think here? Maybe a C library, right? So we have the 64 version. Sorry, DB. So this one, this is a C library. We can directly say how many gadgets this C library has. It's supposed to have a lot of gadgets here. Say over here. So this one command will give us all the gadgets in the C library. It takes quite a long time to discover all the gadgets. And you can see it discovered 100,000 gadgets for us. And all those gadgets are very small. Just so this one, 2 instructions. Some of them could be, this one is 1, 2, 3, 4, like 4 instructions. But most of the gadgets are just 2, 3 instructions. That's it. And in the C library, we can find out 100K gadgets. Okay. Then for our purpose, we already know what is the gadget we're looking for. We're looking for the gadget which is pulp, EDI, then return. Then we just RDI, sorry. We just grab RDI, and let's see. Yeah, we're lucky. We find our gadget. There is exactly the gadget we want. Pulp RDI return. Okay. So this is, you can say this is because we're lucky. You can also say this will always happen because the x86 instruction set is so dense. If you cannot find this gadget in this library, in this program itself, you can also go to the C library to find this gadget. It's just like guaranteed you can find it. Okay. So now we have the gadget's address. We have this one. Now let's say how do we construct this exploit? What we can do is we put this gadget's address here. So first we have the garbage, 4 bytes of garbage to fill buffer, 8 bytes of garbage to fill saved RBP, then 4 bytes the address, which is this one, then another, sorry, 8 bytes of address, then another 8 bytes of address of bin sh, then another 8 bytes of the address of system. Okay, so this looks perfect. So we are going to execute this. Then later you will see there's a problem, and I want you to think, how can we fix that problem? Okay, so now how do we construct this? This one we need to put it into the exploit, the file, right? We're going to do a Python, say print. So first is garbage. How many bytes there? Remember, 12 bytes. Right? 12 bytes, then how many addresses? 3 addresses. So each address is like 8 bytes in this case. 8 bytes. This is 4. That's 7. This is 8 bytes. Yeah, that's 8 bytes. Okay, looks good. Let's see, is there anything else here? Nope. Okay. Then the first thing is the address of our gadget, which is this. So we put it there. It's 63, 12, 40, then just 0, 0, 0. So now you see why I use F3, because there will be a lot of zeros, and those are difficult to bypass. Then what do we have? we have the address of our bin sh, which we already say is I have it here, copied it. So it's actually bin sh address is it's AA 75 F7 F7 FF 7F 0 0. Then we have the address of the function system, which is 1054 E1 F7 FF 7F 0 0. So we're going to write this to the exploit file. Let's do our XXT to check if it's correct. So it's all A's. Then this one. So this one doesn't matter. Looks correct, right? So now we can debug this. We can first run this. In theory, it should work. We just run this 64. Oh, yeah, it will read a file. So we just run this. Okay, we get a second fault. So at least we trigger the buffer overflow. Then let's do a GDB. Let's do a debug on this one to see why this is not working. We have start, and we just go to Valfu. Now we are in Valfu. You can see this is Valfu. We were going to do, so now we do fopen. So we open that exploit function. If the function is the exploit file, try to read the content. Now we already open the file. We try to read the content. We use fread. So after fread, now we should have done the buffer overflow. Let's run a little bit. Now we are at the return instruction of Valfu. We are basically at here. We're at the return instruction of Valfu. So this is where everything starts. So at this point, RSP is supposed to point to that gadget. Let's say if that is correct. Let's exam. Let's exam 3 of those because we need 3. RSP, right? So those are the 4 addresses we posted. The first one is the small thing, which is supposed to be the gadget. Let's exam if that is our gadget. Let's do 5 instructions at this location. Okay, what do we see? We find this is our gadget, right? Pulp EDI return. And where is it? This is actually in the libc init function. But if we go to the libc init function, we disassemble this libc init, you will not find this gadget. You will not find the gadget because we will never start because this is what this function is supposed to start. When you start from here, we will never reach something. This is a full function. You can see the address we have here is 1263. 1263 is actually not the start of a valid. It's not the start of a valid instruction. The valid instruction, the original intentional instruction start at 1262, which is pulp R15 and return. Instead, we're going to jump into the middle of this pulp 15, where we're 1 byte off. And if we jump to there, the CPU will interpret everything, interpret the bytes after that as pulp RDI return. And that's exactly what we want. Okay. So this one is correct. we have the we have the address there. We have this one should be the string. The next exam, if this is correct, we just do x/s to this. See, this is also correct. This points to the string we want. The last one is we just do a print system. You can say this address is also correct. Okay, now we're going to execute this. We're going to do a return. Note that the EIP should be changed. Where is EIP? RIP. The RIP is going to be changed to that gadget address. So now we did a step. Now we are in the gadget. Okay. So next we are going to execute pop EDI. So we are going to pop what we put there to EDI. One step forward. Now the EDI is the value we put there. It points to the string. The string, we didn't put the string there. We only put the address on the stack. And now that address is in RDI. I always keep saying EDI. It's in RDI. Now we're going to do another return. So now this one return, we're supposed to return to the function system. Okay. So we do let's see if it works. It works. Now we are in the function libc function system. Okay. This is supposed to work, except it doesn't. If we continue, you will see there will be a segment fault. So there is a segment fault because this instruction eventually. Okay. So we actually set up everything correctly, but because this instruction, there is a segment fault. If you search this instruction, you will see the problem is this RSP plus 50. And if you search this, you will find out the reason is because what's going on? If you search this, you will find out when you execute this instruction, there is a requirement. There is a requirement that this address has to be, this memory address must be aligned to 16 bytes. That's a hardware constraint. Okay, when you ever execute this instruction, this memory has to be 16 bytes aligned. Without we manipulate the stack, the compiler will generate things that make sure that address is 16 bytes aligned. But because we manipulate the stack right now, we are 8 bytes off because everything we put there is 8 bytes. We put 3 8-byte things there, right? So right now we are 8 bytes off. Okay, so we only need to fix that. Okay, I will give you some time to think how we can fix that.
Quick thing.
Yeah.
When you say 16 bytes aligned, it just means that from the return would be
no. So it means when we where are we? Basically inside the function system, it will use RSP to reference some address, right? So it will be RSP plus a constant. So the constant doesn't matter. What matters is the RSP, which means the RSP should somehow, the addition of them should be 16 bytes, aligned to 16 bytes. However, this constant we cannot change. We can only manipulate the RSP, which means, and what is RSP? RSP is what we control here. It's very obvious, like we are somehow 8 bytes off here. So we need to, so the return address of the system cannot be placed here, which means it has to be placed 8 bytes higher, maybe here. But if we put it 8 bytes higher, what do we put here? What do we put in this 8 byte? This is what I want you guys to think.
So my intuition reminds me of when we were writing our own shell code. We had the option to put in some effective instructions. Well, sorry, ineffective instructions. I guess it kind of provided pseudo nops,
yes.
Which just did some trivial stuff. And it seems like if we got pops in there, we could at least get a free shift of 8 and realign ourselves, since we have to deal with that double register.
Exactly.
Unfortunately.
So Yeah. Does everyone else understand what a field says there? Do you guys? Well, first of all, do you guys understand this part? Do you understand how we return to the system function? Is everyone good?
Can you go back to the terminal for a second? I just want to see
Sure.
the
Sure.
instruction again.
Yeah. Which one do you want to say?
No, I just want to copy the error itself, the instruction at which it fails. So it's.
Oh yeah. Let me copy that to the chat box to you guys.
Hey, Beck, you remember about those registers, right? The XMMs.
Don't recall them.
They're the double wides. That's why we're having
Yeah.
the 16-bit alignment problem. Is those
Yes.
are like the huge ones that are there to run, the extra large operations on 128. I don't know if they're physically 128 bits or if they combine two 64s to do that.
They should be. So those are special registers. The XMM0, that's a special register. Usually we do not see them, but let's search what should I search? X84. Fine. X84 registers. Maybe just the wiki. This one. No, this one don't.
Dr. Joe, you showed us one in the image search that actually was kind of helpful for me because it had
oh
the
yeah.
layout, yeah.
Exactly. So here you can see where is that image? Oh, this one. So see, this is a register. XMM0. That's a register. How big is this one? This is 100. This is 16 bytes. This is 16 bytes, and this one is even bigger. This one is even bigger. So those are registers.
So
yep. Go ahead.
Like how exactly the positioning of RSP breaks the instruction? I guess like.
So it doesn't break. Or why it doesn't break the instruction is because the hardware requires that. The entire CPU or AMD CPU requires that when you execute this instruction, there has to be aligned. Does that make sense?
I'm just having trouble understanding what do we mean by aligned.
It means this address, the RSP plus 50 hex here, is either at an address ending with 0, 16, 32, 64, 48, something like this. It cannot be an address ending at 8, for example, 12, 11. That doesn't work.
Oh, okay.
Yeah.
So like when we do like when we take the number that is going to be there, if we mod 16, it has to be 0 essentially, right?
Exactly. Yeah.
Okay.
Exactly. So because of this, we are triggering a problem, and what we can manipulate is RSP. So Phil's idea is obviously we want to put the address of system 8 bytes higher. Then we need to put something else at this 8 bytes. And what we're going to put here is we can put just a not return or just a return. Actually, just a return will be fine, right? Then we go to our ROP gadget tool and try to find if there is anything give us a not return or just return. You see, we find one. There's a lot of gadgets we have here, which gave us a not, then a return. Of course, in this case, you don't necessarily need a not instruction. Any instruction does something weird, right? Like a EAX plus 1 is equivalent to a not to us in this case, because we're not going to use EAX, right? So in this case, there are so many choices, but we're going to go with this one. So our new exploit we have another 8 bytes here. This is first one, second, and third one. Yeah, it's here. Another 8 bytes here. Let's say then we have EF 1040, then just all zeros. That's our new exploit. Then let's debug this again. Return to, let's say, 64. Yeah, that's it, the what we want. And it's just to here. Continue. We keep running to the point that we are going to return. So now we're going to return. Let's examine our stack. Let's examine like 5 of those. RSP. Then we have those values. This is the address of our first gadget, which is these 2 instructions. This is the strings address bin sh. Okay. This is the address of our second gadget, where it's just a not return or return. If you find a return, there are so many actually. Then this is our third. This is the systems. This is a systems address. And this one, we didn't put it there. It was there before. Okay, we didn't put it there. Now we do SI. We're supposed to return to our first gadget. So this is our first gadget. Pulp RDI return. Then we keep doing it. So now we return again. Now we are returning to our second gadget, which is null and return, right? But now the RSP is changed. Previously the RPSP, the previous one RSP points to here. Now the RSP is 8 bytes higher, and because of 8 bytes, it's aligned. Then we do this one, and we return again. Once more, we are in the system, libc system. We continue from here, we get our share. So this is our share, okay? So we can do this without GDB. We just run this program. It gave us the share. Okay. So that is how we do return to libc at 64-bit version. Okay. So in the homework, you will do something a little bit more complicated. You just need to find other gadgets to set up the registers you need to set. Okay. So any questions here? We didn't inject any serial code, or we didn't inject any code. Okay. We only manipulate the stack in this case. Okay. Anyone else has any questions? Okay, we're good. Okay. Now we are moving to something a little bit more generic. This one we're still doing a return to libc. Next one, we are not going to do return to libc anymore. We just want to do use the ROP to get us a shell, but we're not going to call the libc function system. Instead, we are directly using a system call. So, and we are lucky that this ROP chain tool can directly generate things for us. First of all, let's say we have this ROP gadget, then we can do ROP chain, right? So when we do this, you will find out, it will first print out all the gadgets it find out in this binary. Then it will say, cannot find an instruction they want to find. So basically, after that, it's trying to build a ROP chain. So They just call it ROP chain, but this is a specific ROP chain that give you a share. It's basically setting up those, we did this before. This is basically setting up those registers RDI, RSI, then do a system call to give you the share. So they are going to do the exact same. But however, we only have 67 gadgets here, and this tool is not able to generate that exploit for us because this one is so small, right? This one, you see, only 67 gadgets. The libc library will have 100K gadgets, okay? So what we can do is, I showed you in the makefile, when we compile this program, we are going to compile it as a static. So the C library will be part of this. Then let's check this again, use the static version. Then let's see how many gadgets we have. So this is a static version of this one. Then it takes longer. So we find 40,000 gadgets in the static version because some of the C libraries is compiled into this one. And for this one, we just do a ROP chain, and this tool will give us, see, this tool gave us the exploit. This is the exploit. This tool gave us. Let's take a look what this one is doing. We already know what we're expecting. We're basically setting all those registers. We're doing 64. So let's see. Let's search. x84 system calls. There was a map I showed you guys. Oh yeah, this is a one. This is a one. So this is a one. We are going to do which system call? We're going to do exe CVE, right? That's what we're looking for. So we're going to do the system call number 59, and that number is in register RAX, okay? Then we are basically using the ROP chains, using all the gadgets to set up those registers, RAX, RDI, RSI. RAI should be 59, right? That's what we want. And the RDI should be the string bin sh. And that string can be anywhere. We can even put the string in our exploit because that string is not code. We can put that string in our exploit. It can be on the stack, doesn't matter. And there are two other arguments. We can just set it as 0. The simplest way is just to set both of them as 0. Okay, let's go back to the share code, the exploit. Not share code. This is not share code. This is exploit. Let's say the first thing you notice that is it's doing this crazy thing, right? It's using the same. This is the address of that ROP gadget. It is using this gadget many times. And what is this gadget anyway? This gadget is just add RAX1.
Syscall number.
That's a syscall number. So first we will do a RAX exclusive OR there to set it as 0. Then we're going to just add in 1 for 59 times. So we set RAX as 59. Then eventually we do the system call, and there is a gadget there. Okay, there is a gadget there to do system call. Then you can imagine everything before this is just to set up RDI, RSI. That's it. So this is how this tool generates gadgets. Obviously, you can tell there are many ways to generate the gadgets. Maybe there, for example, maybe there is another to generate the chain. Maybe there is another gadget. Do not add RAX1 instead add RX10, right? There may be one, but this tool doesn't look for that. It's not that smart to chain those ones together to make this exploit a little bit smaller. It doesn't care. So sometimes I believe there could be it could be exploits, but however, this tool cannot generate this. So this is actually an area for research, I think. The smarter ways to generate those exploits. But anyway, in this case, it gave us something like this. Then we just need to make this work. Oh, also note that how big is this exploit? How big is this? So each line is what? How many bytes of each line in the exploit?
8.
It's 8 bytes because each of these is actually the address, right? So we have 59 of this. That's already like 400, 500 bytes, right? Then we have everything else. So this thing, the whole thing is like 600, 700 bytes. Okay, it's a big exploit compared to the exploit we are used to, right? Of course, we're used to put a huge knob there, but that doesn't really count because knob doesn't really do anything for the shellcode ones. So those ones here, everything is important. You cannot replace any of those. And this is like hundreds bytes of exploits. That's why I said in the source code, look at source code, or I say the 100 here doesn't work. I have to make it bigger. So the source code, the new source code I'm showing you is we are running right now is actually 1,000 bytes instead of 100 bytes. Okay. So now let's see how we can use this. We have this. We just copy this. This is just Python code. Then let's just find the editor. Let's say. So maybe this is a 1 actually. Yeah, let me replace this. Okay, we just copy this. This is our exploit. Because this is Python, we need to remove the indent here. You just use any tool to remove the indent. Now, the tool actually gives you should add the padding here. Okay. Let me make this bigger. Okay. The code actually tell you padding goes here. P is what you are going to input. And this is what? This is the first address, return address. Then you add the padding here. And we already know the padding is 12 bytes, right? Yeah, it's 12 bytes. So this is where we added the padding, 12 bytes. So make sure the first one goes to the return address and everything else. And then wait, let's see. We actually put the string directly on the stack here. And we are popping to our AX. Maybe eventually we move it somewhere else. I don't know. Yeah. So now this where then after this P will have our exploit. Then we just print out P. Then that's it. Then we can run our exploit. It will generate this thing. This is our exploit. Then we put this thing into our exploit. Then we directly run our vulnerable program. 64, not 64. This one will not work. This is a dynamic one. This one doesn't have the gadget. We are using a static one. So if we run this dynamic one, it will be segment fault. Doesn't work because it doesn't have those gadgets. If we use a static one, it works. It returns us the shell.
So
yeah, go ahead.
Isn't in runtime the libc still mapped to the address space?
Yes, yes.
So is it mapped to some different address space than the static, I guess?
The static one is a little bit complicated. The static one doesn't necessarily put everything in the libc into your final L file. It usually just put the one you use. And also, when you compile static ones, a lot of the symbol information will be lost in your L file. For example, in the previous example, when you say we do a P system, right? We can get the address of system function. That's because we have the symbol information. Those are dynamically linked. We have the symbol. But when you statically linked, the compiler can remove those, strip out those information because technically it doesn't need that. It only needs to know where is the function I'm going to call. It doesn't have to know what function it is. Does that make sense?
Yeah. So does this tool support maybe some sort of like dynamically. So maybe it does
You
like
can. You
you
can.
can't.
What you can do is you still use that tool, like I showed you before. You use that tool, and you directly get the you directly run that tool on that libc file. Then you find out the address of those gadgets, right?
Oh, okay.
Right. But but that's somewhere you need to be careful because you need to carefully decide. Oh, you need to first say the address you get there is that a runtime address or the address you get there is like offset. If it's just offset, you need to find out at runtime where is the base, everything like that.
I would. Okay, got it. I would think that like e I'm just thinking about like possibility of implementing this as a in the tool. What it could do, right, is maybe put an interrupt at the very beginning, see what got dynamically linked the actual addresses, and then use that
Yes.
information.
Yes.
I'm not, yeah.
That's totally doable. For example, you can say or let's say what can we do? We want to do it as an application layer, right? Let's say somehow whenever your application dynamically load a library, then we can have a dynamic ROP gadget module to find out all the gadgets there, right? But it means that your application needs some signal that to know that this application knows some library. Then probably can hook up something or yeah.
I was more like saying like it would act like GDB. It would stop the program and it would see like what got linked,
Oh yeah,
and then use the linked addresses.
Yes, I believe there are GDB plugins to do that, and also Pun tools can do something like that programmably. Yeah. So let's go back here. Let's go back here. Let's do a GDB of this one to make sure we understand how everything works. Okay. So this is, let's still set the function to valfoo. So we just run this. We just run to the end of valfoo. So right now we are, here we're going to read the file exploit. So the overflow is done. Then we're going to return. So this is where we start to return to all our gadgets one by one, right? So first is the pulp RSI gadget, return. Then we're going to pulp RAX gadget, return. Another move this thing, gadget, return. Then see, we're doing all the gadgets. And though all the gadgets are very small, just two instructions. So far, we are only seeing gadgets of 2 instructions. So keep doing this. Now we are adding the gadgets of setting up the RAX. So right now, which means we already set up everything else. So RDI, we already set up as being SH, the address of being SH. RSI, RDI is already 0. I think those are the 2 we need to set up, right? RDI, RSI, RDX. Yeah, those are the 2 we need to set up. And also RAX. So we already set up all other 3, RDI, RDX, RSI. Those are set as 0 and RDI set as a string. So now RAX, we only need to set up RAX. So we keep doing this. You can say RAX keeps increasing until we get 59. What is 59 in hex? 30, where is it? 3B here. So we just keep moving until we get some where here's 3B. Okay, now we are almost there. Oops, sorry. Anyway, so after 3B, we go to our last gadget, which is system call. Okay, syscall. You can say it's a syscall here. Oops. So syscall. And this syscall, I'm not sure it's necessarily intended to be a syscall in a board. Maybe it is, maybe it's not. But anyway, there is a syscall. So we now return to syscall. Then we are executing our system call execute a new process in sh. That's how we get this share. Okay, so now we have a share. So you can see this is very, very powerful. This is very, very powerful. That's why I keep saying this is one of the most important discovery in system security, software security in the last 15 years. Very powerful. A lot of protections we had before doesn't work anymore. We have a non-executable stack, doesn't work anymore. Of course, we still need to override stack here, but with the help with other vulnerability scaler, it's also possible. Any questions here?
Yeah, and I think at some point I tried reading something about it. I think address space randomization is partially helpful, right? Because sometimes address spaces need to be static, right?
Exactly. So the address space layout randomization definitely can help because what important here is the address of those gadgets. If you move those gadgets around, you are jumping to middle of nowhere, which is not really you want your gadget, right? So that definitely helps. Yeah.
Yeah, I was just saying it's like sometimes from what I was reading, at least some of the libraries they have to be statically linked, no, or some portions of the program cannot be randomized.
Well,
was that the case?
So right now, state of art, everything can be randomized.
Oh, okay.
There could be some old ones because the way they implement it, because the compiler version they're using, they cannot be randomized. For example, when we compile things, you notice that. Where is my file? You notice that when I compile things, sometimes I use no EPI, right? PIE, sorry. PIE is position independent code, position independent executable, right? So that is what we discussed in ASLR. It's related to that. For example, if you compile your program without PIE, then it means your program itself cannot be randomized. The address of those cannot be randomized. But your program uses a lot of other things. Your program uses libraries. Your program uses heap. Your program uses stack. The address of those can still be randomized as long as you enable ASLR at the system level. But your program cannot be.
Got it.
Yeah. And we also look at how to make your program the PIE, right? There is a function like a get BP, get AX, get BX, something like that. Remember? Let's just do an object dump of let's see which program we should use. Let's see. This one looks like. Yeah, remember those functions? Get PC, thunk BX. Those are actually related to the PIE. We studied this when we talked about the ASLR. Yeah. So notice that when I compare the program with no PIE, for example, the program we are using right now, because this is huge, so let's do a grep. This one is huge. Let's do a lawful. So you see these functions, they do not, those lawful or main, we're not using this get PC thing there, right? Because the program we have here is not PIE program. Okay. So these programs will always node it at this fixed address, always at the fixed address. Yeah. So if it's a PIE program, it's actually easy to identify. If it's a PIE program, you can say the address here. No, not really. This example doesn't show that. Okay, anyway, any other questions?
No.
Okay. How is everyone else doing? She, how are you doing there? She, do you understand it?
Yeah, I'm okay. So it's amazing.
It is amazing. I told you, this is like one of the greatest discoveries. I mean, yeah, that guy's a genius. Yeah. Toma, do you understand?
Yeah.
Good. How about Ed? Are you following?
Yeah, follow along.
It's good. Okay. Jackie?
Yeah, I'm following.
Okay, perfect. Who is a selfie stick? Mr. Selfie Stick. Who is that?
It's me, Kamlesh.
Okay. Are you following?
Yeah, I'm doing good.
Okay, good. Serene Cats?
Yeah, I'm
Good. Okay. So for those who didn't finish the format stream, did you guys finish the video? Last week's format stream video? Last time we talked, several said you guys haven't finished the first session of the format stream. Do you guys have a chance to finish that?
Yeah.
Okay.
Yeah.
Good. Okay. So so there will be several homework for you to try this ROP. It's very interesting. There are several tools you can use. I only use the ROP gadget. So you can also try other tools like I mentioned here, like ROPR. Also, next class, we are going to talk about one of the techniques to defeat ROP. And that technique is called control flow integrity. And that technique is actually proposed before ROP, I think. Oh, after ROP. No, I think there was a, so this is a TSEC version. There may be a journal version. There may be a conference version. So let me explain this, very quickly. So one of the techniques is called control flow integrity. It's like when you compile the program, or maybe before you run the program, you kind of know what the control flow should look like. Which function should call which basic block should jump to other basic blocks. You kind of have a basic idea the control flow what should look like. But when you do ROP, it's like we are changing control flow a lot, right? And those control flow is not what we predefined. So control flow integrity makes sure that the control flow can only go to the places you previously defined. So control flow integrity, in theory, stops ROP. However, control flow integrity itself is a very expensive technique. It has to instrument a lot of code. So all the techniques we talked about for the buffer overflow, we discuss how expensive it is. Some of them is very lightweight. Some of them could be very expensive. A control flow integrity is very expensive. However, in theory, it can stop something like ROP, eradicates that technically. So we will talk about the defense. One of the defenses is control flow integrity. And you can imagine a lot of research right now, state-of-the-art research, is how to make control flow integrity very not effective, but efficient, because it's supposed to be very effective, very efficient, and how to make it very efficient on different architecture. For example, Toma and she are working with me on very low-end devices, those embedded devices. How can we do something like control flow integrity or something close to control flow integrity on those very stupid devices? Those are research questions we are, the whole research community is thinking of. Okay, cool. That's actually everything for today I prepared. So like I said, I mean, This class is supposed to be a lot of hands-on there, but because we are not doing in person, so at the first half of the class, I try to make it 3 hours, but now a lot of things I think I finish all the lecture in 2 hours. Then the next hour is supposed to be you do a lot of practice, but you can do it offline. That we don't have to use the class time to do this. Cool. Any other questions? Anyone? Okay, so if no other questions, I see you next week. Take care, guys.
Everybody.
Take care.
Okay.